The purpose of this lab is to analyze the oscillating motion of a mass attached to a spring, model that motion in VPython using Newton's second law and the energy principle, and compare the observed motion to the actual motion of the object. In order to analyze the motion of the mass, I had to first define certain parameters. In the first 5 frames of the video, there was a calibration image. I first used this image to set a length scale by indicating that the equilibrium length of the spring mass system is 0.7 meters. I also set the spring attachment point as the origin of my axes. Then I skipped the first 5 frames to the start of the motion and tracked frame by frame the center of the mass in order to get X and Y position data about its motion. Tracker also created line plots of the X and Y positions, as can be seen. I then posted the X and Y data into Excel and saved it as a CSV file in order to be used for later comparison. In order to be able to understand the coding procedure, we must first understand how our fundamental principles relate. One important value that we need for this lab, the relaxed length of the spring, can be found using Newton's second law. When the mass is at static equilibrium, the net force acting upon it is 0, and since we are assuming that only gravity and the spring are exhibiting a force on the mass, we can set their magnitudes equal to each other and solve for L naught. However, we do not know the value of K, the spring constant. In order to find K, we must draw upon the fact that the angular frequency, or 2 pi over t, is equal to the square root of the spring constant divided by the mass. From here we can rearrange to solve for K. We know the mass of the object, but we need to find t, which is the period of time after which the motion repeats itself. In order to calculate t, I took the times associated with the first 4 troughs, found the 3 delta t's between them, and divided by 3 to get an average. Notice how I'm using the y position data. I will explain why later in the video. Plugging these values into their respective equations, I found my spring constant to be 6.875 newtons per meter and my relaxed length to be 0.12698 meters. The second fundamental principle, the energy principle, states that the changes of energy within a system are equal to the total work done on the system. In this case, our system is the Earth, mass, and spring, and we are assuming that no outside force acts on the system, or in other words, no work is done. Therefore, the change in total energy is 0, and the sum of the changes in kinetic, gravitational potential, and spring potential energy is 0. In modeling my data in VPython, I started out by defining the ball's mass, initial position, and initial velocity. My time step was chosen to be a multiple of the time between frames of my tracker video so that the model motion could be compared to the observed motion. I then entered in my calculated spring constant and relaxed length and defined the length of the spring, its unit vector, and the length of compression or stretching, which are later used to calculate the spring force. I also defined the 3 energies, setting kinetic as 1/2 mass times speed squared, gravitational potential as mg times the y position, and spring potential as 1/2 times the spring constant times the compression or stretching squared. I then set a while loop and defined the initial energies and Newton's second law. I defined my spring force as the spring constant times the amount of stretching or compressing, and pointed in the direction opposite of the L hat vector, which itself is pointed in the direction from the relaxed length position to its current position. I then added the corresponding code needed to update the velocity, position, and spring properties. Then I defined the changes in energies and created arrows to represent the 2 forces on the mass. Finally, I imported my CSV file and set Python to create a graph of the observed motion on top of my models. The result is as follows. Notice how the arrow representing the spring force changes while the gravity force one doesn't. Although my model does not exactly predict the motion of the object, it is relatively close. Possible sources of error include not taking into account other forces such as the drag force and failing to perfectly track the center of the mass in Tracker. I also ran the model to provide me with a graph of the changes in energies with blue representing delta kinetic, red representing delta spring potential, green representing delta gravitational potential, and yellow representing all three added together. The most noticeable aspect of the graph is that the yellow line, the total energy change of the system, remains at zero. If I were to add the values of the red, green, and blue line at any specific time, I would always get zero, satisfying our stipulation that adding all of the changes in energy together would result in zero. Finally, I went back and took a period estimate using the same method as before, but with the x position data instead. As you can see, the period length and calculated k values are completely different between the x and the y. The reason why the y position period is the one to use is because the derivation of 2 pi over t is equal to the square root of k over m is based off of Newton's second law. Since our calculations are based off of our knowledge of the object at equilibrium, and at equilibrium there are only forces in the y direction, we must use the period in the y direction. Thanks for watching.